All right, welcome back to Easy Math with Nick. Today we are on video number 22. In this video, we're going to cover convergence tests for positive term infinite series. So when I say positive terms, that positive term series, that means all the terms in that series are going to be positive. So without further ado, let's get right into it. So the first test we'll be going over today, I have it on the eraser by accident. It's called the nth, no, I can't spell, nth term test. And as we go over these tests, I'm going to give a use case first. So when we use this test, the nth term test, as we'll see, we're going to use it always. This is a great one to start off with because it weeds out a lot of different series that without having to go through so much work, because this test is relatively simple. So this states that if limit n approaches infinity of the a of nth term. So as we go to a, as n increases, does not equal 0, then that infinite series must diverge. So this makes sense logically if we think about it this way. Must diverges. Can't spell. Can't speak. Whatever. No one saw that. But what this means essentially is if we write out like the summation that we're doing here, a of 1 plus a of 2 plus dot 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 a of n minus 1 plus a of n. These terms that we're adding towards the end of our series here have to be very, very close to 0. They have to approach 0 because otherwise it wouldn't converge, right? We wouldn't get a specific value because we would be adding like values that are not 0 at the very end here. So in order to, if a characteristic of a convergent series is that these go to 0. But one thing we don't want to do here is say that the inverse of this is true, which the inverse would be if a of n converges. I'm sorry, no, yeah. No. If the limit doesn't equal 0, I was doing a contrapositive, sorry. If a of n equals 0, so this is the inverse, then it must converge. That's not right. I'm writing it out, but this is false. This is not a true statement. So we want to be careful here in only using, it's not a biconditional. It doesn't go both ways. So just stick with this half of the state of the conditional. The other way doesn't work. So and we'll get to examples of that later on. So the reason, and you'll see that very soon. So that's the nth term test. So what this is saying is, as n gets bigger and bigger, those terms towards the end of the series have to be 0, or have to be approaching 0 for it to converge, or else it's going to diverge. So, but that's if it's converge. It's hard to say because if it does equal 0, that doesn't mean it converges. But if it converges, it has to. Whatever. You kind of see what I'm getting at here. I hate to confuse you more than I already am at the start of the video, right? But that's the nth term test. So don't use the if you negate the statement, it's not going to be true. It doesn't work the other way. Like if it equals 0, then it must converge. That's not true. So okay, enough stumbling over my words. Let's get into an example of the nth term test. This is a nice example. So you have the series 1 over the nth root of e. So if we do the nth term test here, this is going to equal. That's another way to write the nth root on the bottom there, on the denominator, which is going to be, if we just like plug in infinity, I don't know if that feels right to you, but it does to me. What's 1 over infinity? 0. So it's going to be 1 over e to the 0 equals 1. Wait, that's greater than 0. So it must diverge. Series diverges. So that is how you use the nth the nth term test. And this one's a really nice one to start off with because it's just taking that limit as n goes to infinity, which usually is not a very difficult thing to do. Sometimes you have to use Hopital's rule, which is beyond the scope of this video. You should know it, but and we might get to an example where you don't need it, but further on in the video. But there you go. The nth term test doesn't take much work, and it gets you. It gets if it diverges, you can see that very quickly with this test. So you always want to start off with it if possible. The next one that's really nice is the integral test. This one, the use case meets the three conditions below, which we'll get to. These are three conditions below, and is easily integratable. And is, I can't spell, dude. I cannot spell. Easily integratable. Hopefully that's how you spell that, right? And is easily integratable. So if it's something like, just an example where you wouldn't use integral test, if you have 1 over cube root of x squared plus 1, or something like that, I wouldn't use the integral test for that because that would be horrible. Or even worse, something like swap the 2 and the 3 there. Yeah, good luck integrating that, right? So yeah, that's where we wouldn't use the integral test, and we would default to one of the other tests that we would cover. So what are the three conditions though? Condition 1 must be positive. So the series must be positive series. So there must be no negative terms. So, and that leads us to the next one, must be decreasing. It cannot be increasing for this to work. You'll see decreasing for all n that we're working with. And finally, must be continuous. Well, okay, when I say continuous, you're probably thinking, wait a second. So when we do sigma notation, we're adding up discrete values, right? So that's going to be a of 1 plus a of 2 plus whatever, yada, yada, right? Okay, for this condition, we need to, in order to check this, we need to establish a function where we have f of x equals a of x. We essentially make a function that's our a of n. Our a of n term, we just kind of we kind of just make a function out of that. We just replace the n's with x's, and that's a function. And if this function f now must be continuous. It'll make more sense when we get to an example, but this f function must be continuous. And most times you could just tell because it's a polynomial or like an exponential equation, and you already know that it's going to be continuous. But that f of x that we define ourselves must be continuous. And so the integral test itself, if we're starting at 1, we don't always have to start at 1, but we're going to use that for the sake of simplicity here. F of x dx. If it equals some constant c, a real number, of course, if it equals some constant c, no greater than 1, forget I said that, some constant c, then this means it converges. If it doesn't, I'll write it again, if the integral from 1 to b, or wherever we're starting at, where b approaches infinity, because that's how you're supposed to do an improper integral, does not equal constant c, so in other words, the integral diverges, it's going to diverge. So this is why you see now it has to be something that we can easily integrate so we can find this integral. If we can't easily integrate it, the integral test is not going to apply. So that's our use case here. You can integrate it easily, and it meets these three conditions. If it doesn't meet those three conditions, positive, decreasing, continuous, you don't use it. So a good example, a nice easy one, an example that you probably already know is going to converge, but we'll prove it here. Oh, I'm sorry. I skipped straight to the integral. Oops. Let me write it out first. Over to the n. So if we make a function out of what we have inside the sigma here, it'd be f of x equals 1 over 2 dx, which equals 2 to the negative x. So if we integrate that, 1 to b, we have 1 over 2 dx dx. I'm just going to speed run the antiderivative here. Infinity and beyond. Okay. Negative 1 over ln 2. 2. Oh no, my screen darkened. That's not good. Yeah, my battery's about to die. Okay, so we gotta go quick. That's what that means. 2 to the negative x from 1 to b. And so it's going to be limit as b approaches infinity. Negative 1 over ln 2. 2 to the b. We're putting it in the denominator now. Not equals. Plus 1 over 2 ln 2. And as b approaches infinity, 2 over b is going to approach 0. So this whole guy is going to approach 0. So it's going to be 0 plus. We don't care about what this value is, because the value that our integral gets is not going to be the same value as we get from the series. So these are not equal. It just tells us if it converges or diverges. It doesn't actually find a specific value that it converges to. But here, because it does equal a value which is greater than 0, constant, it's going to converge by the integral test. So it's a nice example here. And if you probably already knew this converges because it's a geometric series, right? 1/2 plus 1/4 plus 1/8 plus ... Where like the ratio is 1/2, right? And A1 equals 1/2. So there you go. That you could probably already recognize that. But there you go. That's our first example for the integral test. And I think it's a good one to look out for if you see something that's easily integratable. And so that's the major use case for that one. Pretty cool, right? Let's move on to the next one. Another one I quite like, basic comparison test. Look at that. It's pretty basic, right? Use the word basic pretty loosely here. But no, this is one of the easier ones, and you'll see why. So use case, a main use case, so to keep out in your mind when you're wanting to use this one, is does it look like something I already know? Look like, by in, I mean the series that you have in the question. Like a familiar series. You'll see what I mean by this. But essentially, you want to look for a series that you already know to compare it to. So what the basic comparison test says, there's two parts for it. If for a divergent series, if A of n diverges and B of n is always greater than A of n for all n that we care about, so like 1 to infinity, whatever, then B of n also must diverge. This kind of makes sense logically, right? Because if B of n is always going to be greater than A of n, if A of n diverges, which means it goes on to infinity and doesn't reach a specific value, that means B of n also must diverge. So keep in mind here, we're dealing with positive series, so don't get too caught up by like thinking about how negatives work into this. Don't sweat that. But this does make sense considering, like, if B of n is always going to be greater than A of n, then won't B of n have to diverge if A of n diverges? Yeah, right? That kind of makes sense. So a B of n is going to approach infinity faster, but it's still going to diverge. So, and there's also the opposite for converges, for if we're testing for convergence. If A of n converges and B of n is smaller than A of n for all n, then B of n must also converge. For all n, B of n also must converge. So a good example for this is You probably already know this, but this series that I have here, the harmonic series, this diverges. I'm not going to go over the proof for that right now, but it's a well-known divergent series. So if we wanted to do a basic comparison test, if it looks like something that we could easily compare to 1 over n, that would be a good use of this basic comparison test. So let's say we had n equals 1 to infinity, 1 over n to 2/3. Well, n to 2/3 is always going to be smaller than n for n greater than 1, right? Therefore, if we divide by a smaller number, that's going to make it bigger, right? So 1 over n to 2/3 is going to be greater than 1 over n. And because we know this diverges, and this guy is always going to be greater, this guy must also diverge. Must diverge too. And that's the basic comparison test. So this is it's really that simple, and that's where the word basic comes in, right? If we can make these comparisons based off established series that we already know, it allows us to determine divergence and convergence really easily. So I'd say this is another one of my favorite ones to use because it's really quick, and allows us to determine that quick. Repeating myself, right? I'm at 4% battery. Ooh, I really gotta go quick. Okay, onwards, on to the ratio test. No, limit comparison test. I want to do that one first. Another type of comparison test is a limit comparison test. The reason why these are called comparison tests is because there's two different series that we're looking at in both of these. That's why the word comparison. Okay, so what this states is that if limit is n approaches infinity, a of n over b of n equals some constant c, that's a real number, that's all that means, then both a of n, b of n converge or diverge. Yeah, so what this is essentially stating is that when we take the quotient of the nth terms of both of these series and take that limit as n goes to infinity, and that gives us a constant. If we get a constant out of that, then both of them have to diverge or converge. So this is only really useful if we know one of them, if we know already that one of them is going to converge or diverge. If you don't know either, then it's not really useful. So we tend to pick like a b of n. We build our b of n. That's why b build, right? That's why I like choosing that one, the one that we choose ourselves. We kind of rig it as to make it one that we know if it converges or diverges, so this could apply. So I didn't write the use case for this one, but this is very loose. It could be used for almost anything. But I would say the use case, just so I can say that I said it, any series that looks complicated. Any series that looks complicated. And you'll see what I mean by that in a second. A lot of terms with a lot of coefficients. Any series that looks complicated. So, a good example for this would be, I'll just make this up now. 3% battery. Okay, I'll go down to 2% and then I'll charge it. Go run and get the charger. I have to pause it. Plus 1 cubed. And then we'll do the cube root of, where do I want to take this? And minus 2 squared over, where am I going with this? Okay, I'm just kind of making this up. I'll do 3 to the n over 2n minus 5 squared. Okay. And we'll do from 1. No, not 1. We got to go from 2 to keep this positive. Because if we put a 1 here. No, even if we put a 2 there, it wouldn't be. So we'll go from 3 to infinity. Because see, if I put anything smaller than, any integer smaller than 3 in there, it's going to get us a negative. Oh, no, it's squared. We're squaring it anyway. Forget I said anything, dude. I forgot about the squared. So 1 to infinity is fine. Okay. So when we build our b of n, we want to make it as simple as possible, and as easy to tell if it's going to converge or diverge. So what we the way I like doing this is we just take take our a of n and just simplify it as much as humanly possible. So all these 1s, 2s, 5s, get rid of them. They don't matter. Okay. When we're doing this, we disregard them. So we're just going to have n cubed, 3 to the n, over 2n minus 5. Just make that n squared. And then these cancel, getting us an n. So we have n, 3 to the n. The 3 to the n matters much more, so we kind of just get rid of the n. So you simplify it as much as you could. And so we're going to be dividing by that 3 to the n now. So let's do that. I don't know if this was the best one to do. I think the 3 to the n makes it more difficult than it needs to be. Let me see here. Okay, well, this wasn't the best example. I'm sorry. But kind of just came up with this on the spot. Well, we use this example for a later one because I know it'll be good for that, for the next one. But no, we don't need the sigma anymore. Now we do this. We want to divide it by our b of n because this is our b of n now, right? Equals, no, I don't know why I drew a horizontal line there. Equals b of n. And this was our what? A of n, right? So now we want to divide the two and take the limit as n approaches infinity. So if we want to divide this, we multiply by 1 over it. The 3 of n's are going to cancel. So we're going to get n cubed plus 3n squared. I'm just factoring out the top there. 3n plus 1 over, what's this? Be 4n squared minus 20n plus 25. Well, if we take the limit as n goes to infinity, square terms, we don't really care about these. This guy's going to win the day, and he's going to go off to infinity. So that's not a constant, right? So this is where the limit comparison test wouldn't really work. But you could kind of see the process where we simplify this down as much as we can to get to a b of n that we then divide by, and then we take the limit. And if that limit comes out to a constant, then we know, hey, they must both converge. If this one guy converges and the other guy does, if one guy diverges, the other guy also does. I guess this is also a bad example too, because we know this is going to, well, diverge, right? And we kind of know this by the nth term test, because if we did what? So we have 3 over n equals 1 to infinity. Moment as n approaches infinity, 3 to the n equals infinity, which is definitely greater than, what, 0, right? So that fails the nth term test pretty easily. So yeah, that was just a horrible example. But we're going to use that one for the next one, which is the ratio test. And as for a use case for that one, yeah, something that looks complicated where you have a lot of like exponents going on, a lot of stuff that would like factor into like ugly expressions. So that's sort of when you would use that. My battery is dying here though, so I'm trying to speed up. Next, ratio test. So the ratio test states that if approaches infinity, a of n plus 1 over a of n equals some constant, c, it's a real number, that's greater than 1, diverges. What diverges? The series a of n. Infinite series diverge. If, and you kind of see where I'm going with this now. Plus 1. Equals c. 1. And then converges. And now you could probably say, oh, I'm at 1%. Okay. I'll go charge it. Give me a moment. All right, I'm back. I'm not plugged in just yet, but I'm about to. If I lose this recording, that'd be very bad. But there you go. Okay, and then there was light. Okay. Finally. All right, so where was I? Minor setbacks here. Sorry about that. Oh yeah, if you might be wondering, what if this limit here that I'm underlining, equals 1, then ratio test fails, and we have to go to something else. So a good example, we're going to use this guy again. I promise this is going to be much more useful for now. I'm going to copy him over. I think I could do that. Look at that. Oh, now I could copy him here. How do I copy? I want to put him there now. I could just grab him and bring him down there, I think. Here. Isn't that cool? Come on, you have to admit that's pretty cool, right? And then he's back up here. There you go. All right. Copy some other lines too, but all's well. If we want to use the ratio test for this guy, we know that A of n is that A of n plus 1 is going to be n plus 2 cubed, 3 to the n plus 1 over 2n minus 3, right? Yes. Okay. Squared. All right, so if we divide these two and take the limit as n approaches infinity, it's kind of easy to get the ratio test and the limit comparison test screwed up. But with the limit comparison test, we have to, the difference with that one is we're actually comparing between two different series, one that we kind of build ourselves, the B of n, and with the A of n that we start with. So this one, we don't have to do any of that. It's just finding A of n plus 1, which is just plugging in n plus 1 here, plugging it in there. So that's what we're doing there. So if we take this limit now, it's going to be, let's write it out first. Remember, when we divide a fraction, we multiply by the reciprocal. That's how that works. All right, so some nice things can happen here. Right off the bat, these 3 to the n's cancel, so we're just going to get 3 on the top. And if we FOIL out the top parts, we're going to get n cubed plus, sorry, it should be a 6 n squared plus 12n. If you're wondering where I'm getting this, don't sweat it. I get it from the binomial theorem. I kind of just memorized that. That's a different video, one of my earliest videos. So go watch that. If you're confused, go watch that video. So we have 4n cent. Whoa. I can't speak. 4n squared minus 12n plus 9. Then over here, we get 4n squared minus 20n plus 25 over, and don't forget the 3, right? Don't forget that 3. And then this is just what we had before. By before, what I think, way up there. But. All right, and so as we approach infinity, what's going to happen here? Well, a lot of fun stuff's going to happen. All these n squared terms aren't going to put, all the n terms and the constants aren't going to play much of a role right off the bat. Neither will the n squareds, because the n cubes are going to matter much greater because these grow faster. So we can just disregard the n squared term. So we're going to get, as n approaches infinity, 3n cubed over n cubed equals 3. And this, what, is greater than 1. So therefore, this series must diverge by the ratio test. There you go. All right. So that is the ratio test. When would I use this? Again, if it kind of looks complicated, you could also very well use the ratio test, but more concretely, if you see anything with like an exponential, like 2 to the n, e to the power of n, or like any constant to the power of n, or even like n squared or something like that, it might be worthwhile to use this because, look, as we saw here, we have 3 to the n plus 1 and a 3 to the on the top and 3 to the n on the bottom. That's going to gives us something that cancels very nicely. So that's sort of something to look out for. when we do the ratio test, and that would be a good use case. So finally, last but not least, the root test. You might have noticed one thing I'm not covering in this video is the p-series, because that's a little bit difficult to prove and sort of takes a while. And I like to sort of explain why most of these work. I know I didn't really explain it for the last one, the ratio test, but all the other ones I sort of explained generally why they work. For like, I think maybe I didn't do it for the limit comparison test, but for that one, they must if we're getting a constant, they both must converge or diverge, because if one of them diverged and the other one didn't, we would either get 0 or infinity, because if b of n diverge, it's going to be going to infinity, going. I say going a lot because it's approaching infinity very quickly, but a of n is not. It's converging to a specific value, so you would get 0 in that case. And if you flip the tables, if a of n was diverging and went off to infinity and going, but b of n did not, and it converged, you're going to get infinity over a constant, which is just infinity. So, and that would not be a constant, so that would diverge. No, not necessarily, but the limit's going to be equal to infinity, so the limit comparison test would fail. So, and it wouldn't equal a constant, and so therefore, they must both converge or diverge if we get that limit to equal a constant. So, I don't think I explained that before. So, sorry about that side tangent, but I do want to bring up why that limit comparison test makes sense. For the ratio test, it's a little bit harder to sort of see why that makes sense logically, but I'll leave it up to the viewer to think about that on their own. So, all right, finally the root test. So, sort of similar to the ratio tests and what we're looking for here, but through a of n greater than 1, a of n diverges. Similar if that thing's greater than 1, I could say it equals some constant that's greater than 1, but I think we get the point by now, right? No use in being needlessly formal, unless that's what you want to do. And if it's less than 1, it's going to converge. And just like the other test, the ratio test, if we do get that limit as n approaches infinity of the nth root of a of n, if that comes out to 1, exactly 1, then the test fails and we have to move on to something else, because then the root test is not going to tell us anything. So, a good example for when this would be useful is if we can use case when it's easy to take the nth root. That's as simple as it gets. Easy. Take the nth root of a of n. That is exactly when you use this. Can I take that nth root very easily? So, and it's going to get me something really nice. So a good example of that would be, let's say 2n over n plus 1 to the power of n. Right? This one's a really easy one because look, right? If I take the nth root of a of n, it's going to be the nth root of 2n, n plus 1 to the power of n. It's just going to be 2n to the n plus 1. And if we take the limit of this, as n approaches infinity, it's going to be, if you could technically do Hospitals here, so you're going to get 1 infinity over infinity. And then you do Hospital. Hospital's rule. And that's going to get you, 2 over 1, 2. But that's greater than 1, so therefore this guy must diverge by the root test. So there you go. Those are all the different types of tests that you should be aware of and on the lookout for. In terms of the first ones you should be doing, nth term test is always a good one to start off with. I can't think of a scenario in which it would hurt you by starting off with that, because it's just taking that limit as n approaches infinity. Integral test is nice if it's something that you can integrate. If it's not, too bad, you have to use something else. basic comparison test if the series you're presented with looks sort of similar to something you already know, or looks like, hey, the series is always going to be greater than or less than something I know, then this is when you use the basic. This is when you would use the basic comparison test. Um, Limit comparison test, if you're presented with a series that you're just sitting there staring at like, oh my gosh, I can't compare this to anything, so I can't use the basic comparison test. It looks absolutely horrible to take the integral of, so I can't use the integral test. And it just looks absolutely like I don't want to do this at all. I want to give up and go home. That's when you would use the limit comparison test, because you have a lot of complicated things to work with. That would factor out into like ungodly things, very unsightly, and that's when you would use that, I would say. And for the ratio test, I would say the use case for this is, I'm sort of repeating myself, but when you would have like an exponent somewhere in there, so you would have you would get a scenario in which you would get 3 to the n plus 1, for example, over 3 to the n, like we saw here. That would like cancel out nicely, leaving us with 3. Leaving us with just a constant where we don't even like need to take the limit of that. And that helps simplify things a lot. So that's when I would say the ratio test is a good one to use. For the root test, I know I just kind of said this less than a minute ago. It's when it's easy to take the nth root, because therefore then it's just like, when it's easy to take the nth root, then taking the limit afterwards should be pretty easy as well. So it helps us determine convergence or divergence pretty quickly. So there you go. Those are all the different types of convergence tests. And I think with all those in your arsenal, you should be pretty well prepped to deal with positive term series and testing for convergence or divergence. So maybe in the future I'll do a video on like alternating series and more complicated examples. But that's all I know for now. So thank you for watching. This was Easy Math with Nick, video number 22. And I'll see you next time. So there you go. See ya.